Students, we are going to complete our discussion today on this liquid to solid transformation. So in the last lecture I gave you some idea about eutectic solidification. Today we are going to look at eutectic solidification in a little detailed manner and show you how we can actually use theoretical formalisms to understand the eutectic growth. As I told you, eutectic can have different morphologies, but we have been concentrating on lamellar growth. Lamellar type eutectic is the one which is easy to understand and easy to deal with mathematically also. So now I am going to discuss how eutectic grows using little bit of thermodynamics and also kinetics and show you how things happens. So as I told you, let us first draw a phase diagram which shows eutectic growth. As usual, it is a phase diagram with two terminal solutions. Liquid transformed to two phases alpha and beta at the eutectic temperature. And we are going to discuss only the case for which the composition of the alloy is exactly same as eutectic, that is equal to Xc. Okay, now the eutectic actually grows in a lamellar manner. So I can actually draw this eutectic in a lamellar like. So this is suppose alpha and this is a beta, and slowly I can build up the eutectic lamellae. So therefore there is a planar interface which is not exactly planar, and eutectic is growing with a velocity v into the liquid, this growth front. As you see, this is a lamellar, so therefore internal lamellar spacing, what the way we define also define in the book is like this. This is the lambda, that the thickness of the two lamellae, one is alpha, other one is a beta, and this is the most important characteristics of microstructural characteristics which is used to determine the important mathematical equations. So we obviously this growth is basically possible because of the undercooling of the liquid. As you know, if the liquid is undercooled, then only any phase will grow. So here, as you have seen properly earlier lecture, the alpha growth requires rejection of B because alpha is A rich, as you see in the phase diagram. So this B which is ejected by alpha must diffuse away in front of from the front of the alpha to the liquid, or basically the B which is rejected by alpha will be required for the growth of beta because beta is reached B. So similarly beta growth requires rejection of A. Why? Because beta is B rich. So therefore extra A has to be rejected into liquid, and this A can then be transported to the alpha. Okay. So by using this color arrows, I clearly show you that the growth of alpha requires rejection of B. So therefore B will be transported from the front or the tip of the alpha to the beta region, and similarly growth of beta requires rejection of A, or basically the A has to be rejected in the liquid, and that A can be transported to the alpha and then used for the growth of alpha. So therefore this is a diffusional process. Now as you know, the free energy difference, which is the available energy to the system for its growth, has two parts. One, the free energy corresponding to the alpha, corresponding to the lambda equal to infinity. This when you have very large lambda, the interfacial energy between alpha and the beta is basically almost 0. So that is the interfacial energy corresponding to delta G within bracket infinity, plus when you have finite value of lambda, then this interfacial energy term has to be taken into consideration, and this is the way this energy is evaluated. This is equal to 2 by lambda multiplied by interfacial energy between alpha beta multiplied by the molar volume of the eutectic, where lambda is given in the thing. So now we know that delta G infinity is nothing but delta H into delta T divided by TE. Okay, it is better to write it as delta T0 because that is the undercooling required for the growth. So delta H is the latent heat evolved and T is the eutectic temperature. Now we can plug in this equation. So therefore, when delta G equal to 0, that is where the balance of the free energy because of the heat evolution and the interfacial energies of the alpha beta will give us the maximum, will basically give us the minimum value of lambda. Okay. So that means I can write lambda star is equal to, very simple, that is this, the delta H, okay, let us put it properly, twice gamma alpha beta Vm lambda star is equal to delta H T0 by Te. So therefore lambda star is equal to twice gamma alpha beta Vm Te delta H delta T0. As you see that lambda star, which is the critical value of lambda for which this delta G becomes 0, is inversely proportional to the undercooling, okay, and directly proportional to the interfacial energy. So as we see, if I have to draw the free energy versus composition diagram to show you this aspect, let me just draw it and show you. Suppose this is G, okay. So liquid, let us suppose liquid has a free energy curve like this, this is GL, okay, and the free energy of the alpha, free energy will be alpha, let us write down alpha in a color way. Free energy of alpha is, when lambda is infinity, is this. So free energy of beta when lambda is infinity like this, and if I draw a common tangent, that is what gives me the equilibrium compositions of the alpha and the beta when lambda is very large. But as we know, in the real system lambda has a finite value, it cannot be infinity. So therefore, because the lambda will increase the free energy by this amount, that means that corresponds to the shifting of this free energy curves up. Let us do that. I will do using a color chalk. So this is what it is, let us suppose, or let us suppose try it this way. So this is dotted as you see here. So G alpha when lambda equal to lambda some value or lambda star, okay. Similarly this is no, okay, this is beta, G beta lambda equal to lambda star. So now if I draw a common tangent between all three of them, I will let us to put it together. As you see here, this becomes XC because this is XB line, and this is a little bit change of the composition of alpha beta. So that is what actually equilibrium will look like for lambda has a finite value, correct. Now this explains why that term 2 alpha beta gamma alpha beta Vm by lambda needs to be, how this needs to be added into the free energy composition diagram, okay. Now question, let us look at how the actually growth happens, what is the mechanism of growth. As I already discussed, the growth is basically because of the diffusion of the atoms from the tip of the alpha to the tip of beta and vice versa. So therefore for the growth to happen, there must be sufficient compositional gradient develop between the tip of alpha to the tip of beta for the B to be transported. Similarly, for the A to be transported, the compositional gradient must develop in between the tip of beta and alpha. So, if I basically do a little bit of calculation, as you see, this V is basically proportional to dC by dl, okay, or rather let us like dCB by dl, where the C, this is, you can write down even better way, xB, okay, this is the xB corresponding to mole fraction of B, and dl is the distance. So, therefore, this tells you the compositional gradient. So, therefore, we can write down B is basically a constant k, this is basically has to be proportional to d diffusivity dxB dl, right. This must be written like this, correct. So, now question is this, in a system like this, as you clearly see, the composition ahead of the alpha and ahead of the beta is basically same. This is equal to xBe, right, xBe as you see here. That means the interfacial compositions, or rather let me write down this way, this is the composition, interfacial composition of the tip of alpha is equal to is xBe. Similarly, interfacial composition in the tip of beta is xBe, because this is the common tangent, though therefore, the solid compositions is at xB alpha, okay. Similarly, solid composition is xB beta. This is in equilibrium with the composition of the liquid given by xBe. So, therefore, in front of the both the alpha and beta, compositions of the liquid is same, there is no compositional gradient available, but for the growth to happen there must be a composition gradient created. So, how we can actually do that? Let us little bit reformulate this diagram, and so that we can understand better way, but we keep it this one same. So, basically velocity of the interface is equal to a constant k1 multiplied by diffusivity d in the liquid and multiplied by the compositional gradient. We need to find out what is the value of this compositional gradient, then we can actually find out the value of V. To know that, we have to basically modify these constructions. How we can do that? Let us do it properly here, okay. So, let me do it in a little bit different manner, okay. What I do is I draw a diagram like that, okay. So, that is your beta, then alpha, okay, then is beta again. So, now if I plot it, if I plot these things properly, if I plot these things properly a little bit, okay. So, let us suppose this is my GL, okay. Now, as you clearly see, this is my, okay, as you clearly see, this is my the different lamellae alpha, beta, alpha, okay. So, to do that, let me see how we have done in my book. To do that, yes, let us, it has to be changed little bit, because otherwise it will not look nice. So, I make it a little bit bigger, so that it looks better, okay. So, now question is this, how you are going to draw this such a kind of things? You can draw such a kind of things by using again phi and g of the alpha and beta. So, phi and g of the alpha will for the infinity will look like this. This is alpha when it becomes infinity as we have drawn. So, this is your again beta infinity. So, we are shifting these things because of the finite values of alpha like this. So, this is my g alpha lambda star as we have done. This is your g beta lambda star. So, if I draw the common tangents here, this is one, okay, and then this is another one. So, as you clearly see, the compositions, equilibrium compositions are given by, at the tip of the alpha and beta are given by these dotted lines. So, this is equal to xp liquid beta, this is equal to xb liquid alpha. Why? Because what I am doing? I am doing a common tangent between the G alpha when x lambda is equal to lambda star with G liquid. That is what has to be done. This is what exactly I have done. In this case, actually, because they are lying on the same common tangent between all of them, so there is no driving force available, but here it is not the case. Here actually the common tangents cannot be drawn. Only thing we can draw is tangent between common tangent between GL and the alpha, again G beta and the alpha, and by doing that I can find out the equilibrium composition at the tip of beta, equilibrium composition at the tip of alpha. So therefore, this compositional difference is what is basically existing between alpha and beta tip in the liquid, and that is what is driving the transport of the beta. So we can write down this equal to K1 dl delta x by, and this is equal to your lambda as we have drawn here. This is what it is. We can always assume that the diffusional distance is basically equal to lambda. Remember, this is basically not a exactly correct expression. Why? Because compositional values will depend upon exact value of lambda. Not only that, it will depend upon where actually we are lying. We are lying here, we are lying there or there, wherever. It depends on the exact location of the interface. We are not doing that because we are doing order of magnitude calculation. Therefore, we are not doing that. So that is what it is. So V is equal to a constant K1 multiplied by dl into x delta x is the compositional difference. So delta x is nothing but, you can write down xp alpha liquid alpha interface minus xp liquid beta interface. That is the compositional difference which is driving the diffusion to happen across the sideways. So now, as you know from the phase diagram, okay, you can actually do that. If I have drawn only the phase diagram, yes, let me draw only the important part. As you know, the phase diagram allows you to convert this delta x to delta t0, okay, delta t, okay. So let me just draw the important lines. This is my TE, okay. I am drawing only this line. Remember, this equal to lambda to be equal to infinity. So if I extend these lines, okay, that tells you the compositional difference from the alpha and beta interfaces, okay. This is the compositional difference between these two. That actually can be written at x is 0, okay. So when lambda is very high, this is the compositional difference should exist between these tips, but when lambda is equal to lambda, so what will happen? This will go down actually. So temperature will simply go down, or let me see how we can draw it properly. That is very easy to draw, okay. Obviously everything will go down. Why? Because when the lambda is finite, lambda is basically finite, then what will happen? If lambda is finite, and then there is a problem of everything, temperature will go down, as this is the effect of interface. As the interface is becoming, energy is higher, delta T will decrease. This is lambda equal to lambda. So we can, this is what is the melting temperature eutectic. Now if we extend that, then this is what is become delta x. So as you see here, delta x is basically a constant K2 into delta T, correct? That is what you see here. So we can write down that. So therefore V is equal to K1 into K2 dl delta T by lambda. Now we also note that this delta x is basically is a function of lambda. Why? Because as you see, when the lambda is very large, then it is equal to delta x 0. This is what it is. So, but when lambda x, because that means what, when lambda will become to lambda star, then it is equal to delta x 0. Okay. Now, when lambda is a finite value, then this value will decrease. So, therefore, we can write down delta x is equal to delta x 0 multiplied by 1 minus lambda. Now, if I do the things properly, then this v will be equal to k1 k2 dl delta t 0 multiplied by that factor, okay, 1 minus lambda star by lambda divided by lambda. That is what you can write down, correct. So, now we can actually do the math properly. If I take the equation from here to there, okay, that v is equal to k1 k2 dl delta t 0, okay, we can write down that's equal to 1 minus lambda star by lambda divided by lambda. Now, if we do the maths little bit properly, you will find out b lambda square is equal to k1 k2 dl delta t 0 and a factor lambda minus lambda star. So, this can be treated as a constant C1. So, that is why b lambda square is basically equal to C1. So, once you know the v for a particular level of undercooling, we can calculate what is the lambda, or rather it is other way. If we know lambda, we can calculate v at a particular level of undercooling. That is what it says. So, for the eutectic growth, this relationship is very important. Although this relationship can be obtained in a very general mathematical manner using Jackson Hunt, what he has done I told you in the last class, but we can simply assume many things and get that equation very easily. So, similarly, one can actually get this also, constant C2. But you must see one thing, the basic equation which is related to v lambda and delta t is given at the top, okay, and in that equation only variable which you know is a delta t, that is the undercooling, which can be measured in experimental. Things which you do not know is basically apparent is a lambda, and so therefore only knowing delta t 0 will not give us the answer of v and lambda independently, correct, because this is a single equation. We have two variables v and lambda for a particular value of delta t 0 or delta t, okay, undercooling. So, question is this, if I have to calculate v and lambda independently, then I must have another equation relating v and lambda. That is not available to us, unlike density growth, here it is not available. So, what we normally do, we try to assume that eutectic growth happens at the minimum level of undercooling. So, we try to minimize the v velocity with respect to, or maximize the velocity with respect to the delta t. That means the growth is maximum at the undercooling level. So, that means we need only finite level of undercooling for the growth to happen. Now, that is not correct. So, therefore, it is better actually we can actually look at the microstructure after solidification, find out the lambda, and then using delta t 0 we can find out what is the possible v, velocity of the interface. Okay, so that is possible, but you have to remember that one thing, the lambda which was there during the growth may not be retained when you solidify it completely, because there will be coarsening of the alpha beta lamella. Okay, so that leads to change of lambda, or actually change of overestimation of the lambda. So, this overestimation will lead to underestimation of the value of, sorry, obviously overestimation means higher value will lead to underestimation of value of v. So, therefore, it is not possible to measure exactly the velocity of the interface or calculate that using this equation. What better method is to do is that take a system in which we can actually observe when the eutectic is growing at a certain velocity, we can observe these lamellae and then measure the value of lambda perfectly when it is in contact with the liquid, and use that value at a particular level of undercooling to calculate v. So, finally, it boils down to the important aspect that eutectic growth is still is not a fully solved problem. We can actually only see that eutectic growth is a undeterministic problem in the solidification literature. You know, as I told you, the major undercooling part is the delta TD. Okay. So, delta T has two parts, delta TD is the diffusional part, and obviously delta T and the curvature part, which is basically known as delta TR. Why curvature part? Because interface is highly curved, and because of the curvature of the interface, there must be undercooling related to that. And this, out of these two are the major aspects of undercooling which are required for the interface to grow. And sometimes people also add another part which is known as interfacial undercooling, but this value is basically required when the eutectic growth is, this value is basically correspond to the atomic jump from the liquid to the solid, the undercooling required. Normally it is very low when the interface is kind of a rough, so the atoms can easily move, jump and do that. But when the interface is very faceted, like in aluminum silicon type eutectic, this value is very high, and one must add this particular component to the total undercooling equation to do that. So, in actual experiment we cannot measure each of these, we can estimate later on theoretically, we can measure total undercooling and plug in there in the velocity versus lambda relationship and get the velocity in the form of some values. So, as you see here, the eutectic growth is much more complex than can be thought of. As compared to dendrites, eutectics more widely, also equally widely observed in the microstructures. So, therefore, it is important that we know their growth very well, but unfortunately those theories are still not developed. Okay, there is a requirement of develop new theory for understand the eutectic growth. In future probably we will get to know these theories well, but for the time being you need to only understand how a eutectic grows in the liquid, whether can you use thermodynamic and kinetic aspects to understand their, or to basically obtain mathematical equations of the growth rate and other aspects. So, in the next lecture I am going to discuss about a little bit about what happens in the casting, and then move ahead for the solid to solid phase transformations.